Myself, Dr. Naresh Kumar, Associate Professor, Department of Mathematics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today, I want to discuss the topic linear differential equation of nth order with constant coefficient. I want to discuss in detail how we can find a solution of a linear differential equation of nth order with constant coefficient. Which method we are using in a linear differential equation of nth order with constant coefficient. So I want to discuss in detail. Here we apply a important method that is known as a y is equal to CF plus PI method. So here how we can apply CF plus PI method in a linear differential equation of nth order with constant coefficient. So my video main focused on solving a linear differential equation of nth order with constant coefficient. N is any number more than 1. N is any number 2, 3, 4 or n order. So we discuss one by one method. First of all, I want to discuss that what is linear differential equation of nth order with constant coefficient. So here we are giving a differential equation of n order with constant coefficient. So this is the main differential equation which we are studying about the differential equation that is given by 1 here. So what is this one? In this differential equation, this is the differential coefficient of n order. This is first term. And before this differential coefficient, there is multiply by 1. There is no number before nth order differential coefficient. And then 1 by 1 in each term order is decreased. Here is n order, in second term n minus 1, third term n minus 2 and last term is no order. There is only y equal to q. Right hand side is some function of q. Q is the function of x here. Because every derivative there is independent variable is x. So q is the function of x here. And here multiply in each term with derivative is p1, p2, p3 and pn. These are constant numbers. And q is the function of x here. Q equal to say here fx. This is known as a linear differential equation of nth order with constant coefficient. But here we will discuss linear differential equation of second order with constant coefficient. Not taking higher order, only second order differential coefficient we are discussing in our topic. How we can solve a second order linear differential equation with constant coefficient. So here d2 by dx2 in our question, we see that there are only 3 terms in left side, d2y over dx2, and there is 1 in multiply with this derivative, second order derivative, d2y over dx2 multiply by 1 and dy dx multiply by p1 and y multiply by p2. Here p1 and p2 are constant. And in right hand side is q. Q is the function of x. Q equal to fx. We can say that q is fx. And p1, p2 are number. So in detail, we are solving today equation 1 that is known as a linear differential equation of second order with constant coefficients. So here we are giving several examples of linear differential equation of second order with constant coefficient which are given as follows. So here example first is d2y over dx2 plus 5 dy dx plus 6y equal to e to the power x. This is the second order. Here is the derivative of second order. This is the first order derivative. There is no order and this is the function of x. So here no multiply is only number are there. In each term in multiply is number are there. First is 1 here. Here is 5 and 6. So all numbers are in multiply. So we can say that this differential equation is known as a linear differential equation of second order with constant coefficient. This equation can also be written in this form. How we can write this form? So d2y over dx2, we can write this d square y. Okay, because d over dx is d. Now dy over dx is dy, and d2y over dx2, this is d square, and d over dx is capital D. These are representation here. After putting these values here, then we can write this in this form. This is also differential equation of second order with constant coefficient. This is second example. Similarly, this is third example. d2y over dx2 plus 6dy dx plus 8y equal to x square. So here we have given three examples which is known as a linear differential equation of second order with constant coefficient. Here we will discuss in detail how we can find the solution of linear differential equation of second order with constant coefficient. So here we take general equation d2y over dx2 plus p1 dy over dx plus p2y is equal to q. This is equation 1. This is general linear differential equation. This is general linear differential equation with constant coefficient. Equation with constant coefficient. Okay, general linear differential equation with constant coefficient. So now we want to solve the equation 1. So here solution of equation 1, we will use here method y is equal to CF plus PI method. So CF, what is CF? CF is complementary function. PI is particular integral. There are two parts. There is two part of the solution. Number one part 1 of solution, that is CF, complementary function. And part 2 part of the solution is PI, particular integral. When we are adding both solution CF and PI, then we get y is equal to CF plus PI, that is complete solution. This is complete solution of the given linear differential equation of second order with constant coefficient. Here we will discuss second part of solution. Second part mainly our focus to find second part of the solution. Particular integral. How we can find particular integral of a linear differential equation with constant coefficient. So basically particular integral depend on right hand side function. Right hand side function of the equation is q. Q is the function of x. If q is changed, then particular integral is changed. So one by one we have discussed how we can find particular integral. So there are several cases arise here. If q is e to the power ax, then different case. Q is x square, then other case. Q is cos ax or sin ax, then other case. So there are several cases are there. We are discussing one by one cases according to value of q. Here we are discussing. So here we are taking this equation d2y over dx2 and p1 dy over dx plus p2y equal to q. This is same general equation 1. This is general equation 1. Formula for particular integral. Which formula we are using to find out the particular integral, that is very important. So here we are using the formula for particular integral, that is pi equal to 1 upon fd into q. 1 upon fd. Fd in our question there is some function in d. Our equation is type of this fd into y is equal to q. This is the type of the equation. Fd means some function in d. Y is dependent variable equal to q, some function of x. So here this fd, I am taking here this fd 1 upon fd into q. This is the particular integral. This is equation 3. We will discuss here several cases depend on given function q in RHS of the given differential equation, and also we will solve problem based on case 1. So here First, case 1 is q equal to e to the power ax. This is case 1. E to the power ax means there is some exponential function. Here is exponential function here given. Exponential function is given. Okay. So here e to the power ax is an exponential function where a is a constant, may be positive or negative. Any type of constant is there. E to the power, suppose e to the power minus x, e to the power minus 2x, e to the power 2x. Any type of function may be there. So now apply the formula of pi here. Which formula we are applying here for finding particular integral? So formula is pi equal to same 1 upon ft into q. Pi is equal to 1 upon ft into q. Q is e to the power ax. This is basic formula to find out particular integral. So we are solving here problem based on this case here next. Now apply condition. Which condition we are applying here? So condition is here now here putting d equal to a. D equal to a in fd. We have given here fd and putting d equal to a in fd. Then we find fa. And fa is not 0. This is the condition. If fa is not 0, then pi is complete. So here we discuss one problem. Problem 1 based on case first. Q equal to e to the power ax. What fa is not 0. Here a putting d equal to putting a in fd. Putting here d equal to a in fd means fa. fa is not 0 here. fa is not 0. So here we solve the problem this is depend on case 1. d2y over dx2 plus 5 dy over dx plus cy equal to e to the power x. This equation can be written as d square plus 5d plus 6y is equal to e to the power x. How we can write this? This result is d square y and plus this 5dy and plus 6y equal to e to the power x. So y is common and here is d square plus 5d and plus 6 equal to e to the power x. This equation can be written as. Now solution. Here we are discussing in deeply solution how we can find solution of equation 1. Equation 1 is known as a linear differential equation with constant coefficient. This equation is the example of question of linear differential equation with constant coefficient. So equation 1 can be written as, we can write equation 1 this type here. d square plus 5d plus 6y equal to e to the power s. This is 2 equation. Now we can find the solution of equation 2 in 2 parts. Part 1. Here is part 1. Part 1 is CF, complementary function. Part 1. There are 2 parts of the solution. Part 1 is complementary function. First, to find complementary function, putting q equal to e to the power x. Q is here e to the power x. Here q is given. Q is e to the power x. Here q is e to the power x here. Okay. So e to the power x, q equal to e to the power x in right hand side of the question, that is taking 0. Then from equation 2 becomes. This equation becomes this. D square plus 5d plus 6y equal to 0. This equation 3. Right hand side here we are putting right hand side 0. When we are putting right hand side 0 means we putting the value of q is 0. Then we can find CF. Right hand side must be 0 for finding CF of the question. So equation is this. After putting right hand side is 0. Now putting d equal to m and removing y from equation 3. Removing d equal to putting m and removing y from equation 3. Then we get an auxiliary form. Auxiliary form a differential equation. A equation which is writing in m. M is variable there. d equal to putting m, then our equation must be this: m square plus 5m plus 6 equal to 0. This is auxiliary equation. This is known as a auxiliary equation. Auxiliary equation. After putting d equal to m, this is known as a auxiliary equation. So now now factorizing of equation 4. This is an auxiliary equation. We are keeping here factorization. So here is m square, put here 6 is factor, here 6. We are doing factor 6. 6, 3, 2 is 6. And here is 5. And 3 plus 2 is 5. So we are applying this factor. Okay. Last number is 6. So we multiply 6, 3, 2 is 6. And second number is 5. So we are adding these factors 3 and 2. 3 plus 2 is 5. So here m square plus 3m plus 2m plus 6 equal to 0. Here taking m is common. So m is common here, m plus 3 plus 2 common, m plus 3. M plus 3, this bracket are same here. If bracket are not same, then our factor is wrong. But bracket is same, then our factor is correct. So m plus 3 taking common, then we get m plus 2 equal to 0. So here if m plus 3 equal to 0, then we get m equal to minus 3. And m plus 2 equal to 0, then m equal to here minus 2. So we get here value of m is minus 3 and minus 2. Roots of equation 4. Roots of equation 4 are different here. So we here apply using formula for CF. If roots are different, which formula we are using here? Which formula we are using here to find the CF of equation 4? So CF formula is this. CF equal to C1 e to the power m1x plus C2 e to the power m2x, where m equal to m1 and m2 are roots. m1 and m2 are roots. Are different roots here. Different roots. m1 and m2 are different roots. So CF equal to C1, now putting value of m1 and m2. C1 e to the power minus 3x plus C2 e to the power minus 2x. Minus 3 and minus 2 are roots are there. So I am putting here m equal to minus 2 and m equal to minus 3. This is m1, this is m2, and this is m1 here. This is m1. So putting here, this is the complete CF of equation 4. Now finding PI, particular integral. Apply here case first and condition first. So in PI we are applying condition first and case first. What is case first? We are solving here particular integral formula. We are using here formula of PI 1 upon FD into Q. 1 upon FD into Q. This is the formula of PI. So here Q is e to the power x. I am putting here e to the power x. 1 upon FD. FD is here FD. FD is here d square plus 5d and plus 6. This is FD. Function of d here. FD is this. So we are taking here FD 1 upon d square plus 5d plus 6 into e to the power x. Now comparing here e to the power ax equal to e to the power x. This is given in question. This is general function q. So here then we get a equal to 1. We find a is 1. Putting d equal to a. D equal to a is 1, so d equal to 1 in 5, in this equation 5. Then we get here pi equal to 1 upon, this is not there, 1 upon d square plus 5d plus 6. So putting here 1 upon d, putting d equal to 1 here, d equal to 1. So 1 upon here 1 ka square plus 5 into 1 plus 6 e to the power x. So here 1 plus 5 plus 6, this is 1 upon 12 e to the power x. This is wrong here. So here this is the complete PI of equation 1. Now complete solution of 1 is y equal to CF plus PI. We apply here formula y is equal to CF plus PI. So here y is equal to CF. CF we are writing C1 e to the power minus 3x plus C2 e to the power minus 2x plus Pi. Pi is this 1 upon 12 e to the power x, this 6. This is the complete solution of the given linear differential equation of second order with constant coefficient. If q is equal to e to the power x and putting d equal to e to the power x, compare with e to the power x with e to the power ax. Here a is 1 and putting d equal to 1, then fd is not 0. Fd means d equal to a putting here. D is 1 here. So f1 is not 0. Then our answer is complete. So this is case 1. When fa is not 0, then case 1. If fa is 0, then cases 2 arise there. Now apply case 2 to find Pi. What is case 2? Putting here d equal to a. Q is here e to the power ax. Same e to the power ax. And putting d equal to a in our given differential equation, then fd equal to fa, d equal to a here, putting, then fd equal to fa equal to 0. This is the case 2. Okay. Problem 2 based on case 2. I have defined this case 2. Condition of case 2. So here question is solve d2y over dx2 minus 3dy dx minus 10y equal to e to the power minus 2. So comparing this question is same as this d2y over dx2 and plus p1 dy over dx and plus p2 y is equal to e to the power ax. This is same as question this. p1 p2 are constant, this p1 and p2 are number. This is same equation is this. This equation can also written here d square minus 3d minus 10y equal to this. D means dy dx. D square means 2 time differential d2 over dx2. And d means 1 time differential d over dx. So we can write this equation is this type. Now solution. This is the question and solution. d2y dx2 d2y over dx2 minus 3 dy over dx minus 10y equal to this e to the power minus 2x, this equation 2. And equation 1 can be written as d square minus 3d minus 10y is equal to e to the power minus 2x. Now, so here also we find the solution of this differential equation in two parts. One part is complementary function, other part is particular integral. Because here q is given. If q is not given in our question, then we find only one part, complementary function. We cannot find particular integral. Particular integral is 0 if q is 0. I have discussed in last videos, if q is 0 in our question, then pi is 0. Then pi is 0. We cannot find pi. So here in our question q is given. So there are two parts of the solution. One part is complementary function, other part is particular integral. So first we find out the CF, complementary function. So first to find complementary function, what we are doing here, putting q equal to e to the power minus 2x. Q is this here in our question, that is taking 0. Then from equation 2 becomes this. D square minus 3d minus 10y equal to 0. This equation 3. Where fd, what is fd here? Fd is d square minus 3d minus 10. This is fd. Our equation is fd into y is equal to q. This is type of equation. This is type of equation. Fd into y is equal to q. Now putting d equal to m and removing y from equation 3. D equal to m and removing y from equation 3. Then we get an auxiliary equation. So this is an auxiliary equation. Equation 5 is an auxiliary equation. Putting d equal to m here and y removing from the equation 3. So m square minus 3m minus 10 equal to 0. This equation 5. Now factorizing of equation 5, then we get here. So here is last number is 10. Last number is 10. 10 multiplied by 5 into 2. And here is minus 10. Minus 10 means minus. So here is 3. 5 minus, here is 3. 5 minus 2. Subtracting these numbers here. So we are factorizing here m square minus 5 minus 2 m plus 10. Not here minus 10. Here is minus 10 equal to 0. So now here m square minus 5m plus 2m. Multiply here minus sign minus 5 plus minus plus 2. So here multiply here. Now we get m square minus 5m plus 2m minus 10. Now here m is taking common. M is taking common, m minus 5 plus 2 taking common, m minus 5 equal to 0. So here bracket is same. M minus 5 is common. So m plus 2. So here if m minus 5 is 0, then m equal to is 5. So this is value of m1. And m plus 2 equal to 0. If then m equal to is minus 2. So this is value of m2. So m equal to m1, m1 minus 5, m1 plus 5, and m equal to m2 is minus 2. So minus 5 and minus 2 are roots. Roots of an auxiliary form are different here. Using formula for CF if roots are different. So this is basically formula for CF here. CF is equal to C1 e to the power m1x plus C2 e to the power m2x. So CF is equal to C1 e to the power m1 is plus 5x, and C2 e to the power minus 2x. This is the complete solution of CF. This is complete complementary function of equation 1. Now, second part of the solution is particular integral, PI. Short form we can say that is PI. So now finding PI, apply case 2 and condition 2. Not condition 1 apply. So here condition 2 apply, here case second. So PI is equal to 1 upon FD into e to the power AX. This is general formula for particular integral. 1 upon FD into Q. This is formula is 1 upon FD into Q. Q is e to the power AX here. So 1 upon FD, d square minus 5d minus 10, e to the power minus 2x. This is equation 6. Comparing here e to the power AX equal to e to the power minus 2x. This is general Q, this is given Q. This is the value of general Q, e to the power AX. This is the value of given Q, e to the power minus 2x. After comparing here, we get a equal to minus 2. Now putting d equal to a is minus 2. So putting d equal to minus 2. What do we have in here? Here fd equal to, this is d square minus 5d and minus 10. Now d equal to putting here minus 2 ka square and minus 5 into minus 2. Here is 3. Wrong. So here is minus 3 into minus 2 and minus 10. So here minus plus 4 plus 5, 3 2 just 6 and minus 10. 10 minus 10 equal to 0. So I am writing here, apply condition 2. Then FD equal to FA. FA equal to F minus 2. This equal to 0. Here FD equal to D square minus 3T minus 10. FD equal to putting, here putting D equal to, putting D equal to minus 2. So here F minus 2 equal to minus 2 ka square minus 3 into minus 2 minus 10. So here 2 minus 2 ka square plus 4, 3 2 ja 6 plus 6 minus 10. 10 minus 10 equal to 0. So here F minus 2 is 0 or FD is 0. Then particular integral is not complete here. What we have been apply again condition 3. Function e to the power minus 2x taking to the left side of pi and putting d equal to d minus a here. D equal to d minus a and making binomial. So now finding pi, apply case 2 and condition 3. We are applying here condition 3. Pi equal to 1 upon fd e to the power ax. Pi equal to 1 upon d square minus 3 minus 10 e to the power minus 2x. This is the value of q. Q is e to the power ax. This equal to e to the power minus 2x. So this function taking left side. This function taking left side. E to the power minus 2x taking left side. And their remaining function is 1. This function goes to left side in multiply. And putting d equal to d minus 2 when we are taking this function to left side. So this function comes here and d minus 2 ka square minus 3 d minus 2 minus 10 into 1. So after opening this d square plus 4 perfect square, we are opening the perfect square of d minus 2 ka whole square. So here is d square plus 4 minus 4d minus 3d plus 6 minus 10. So here 6 this cancel to this and next here minus 7d. Pi equal to this is left side. This function goes to left side here and here is 1. So here d square minus 7d. This equation 7. Now equation 6 apply binomial theorem. Then we take lowest power of d in denominator of pi is common. In equation 6, 6 not 6, 7. Apply binomial theorem. Then we take lowest power of d in denominator of pi is common. So lowest power of d means d ki power 1. So minus 7d is taking common. Here minus 7d taking common and that is plus 1 minus d square upon 7d. So d by 7 into 1. We are taking this in numerator. 1 minus d by 7. 1 minus d by 7. We are writing here this is 1 minus d by 7 whole to the power minus 1. So here taking minus 1 and into 1. Now opening this here minus 1 upon 7d. Here 1 plus this is formula applying here 1 minus x to the power minus 1. 1 plus x square plus x cube and plus this up to infinity. So here we are using this formula 1 plus d by 7 plus d by 7 ka square and into 1. Now multiply by this constant to this bracket. In above equation function is fx is 1 here. So now multiply 1 in bracket then we get pi equal to e to the power minus 2x into 1 upon minus 7d and in bracket 1 and d1 d square 1 and plus this. So now here we know that differential of dy dx of 1 that is 0. d2 by dx to 1 that is 0. So here this result are 0 here. So we are writing here only 1. dn is 1, d cube 1 is 0, d square 1 is 0, d1 is 0. All elements are 0 here. So we get only this one here. So now here pi equal to e to the power minus 2x 1 upon minus 7d into 1. E to the power minus 2x 1 upon minus 7, 1 upon d into 1. Here d is known as a differentiating with respect to x. D means d over dx here. And here 1 upon d represented integrating with respect to x of function fx. So here d1 equal to d over dx of 1 is 0. So now here 1 upon d means integration. 1 upon d of 1 means integration 1 with respect to x here. Then we get x. Not adding constant. So pi equal to e to the power minus 2x 1 upon minus 7d into 1 equal to integration of 1 is x. So minus x e to the power minus 2x by 7. This is pi. Equation 8 is complete pi of 1. Now complete solution of 1 is y is equal to cf plus pi. So y is equal to c1 e to the power 5x plus c2 e to the power minus 2x plus minus x into e to the power minus 2x by 7. This is complete solution of equation 1. Now problem 3 based on case 2. d2y over dx2 minus dy over dx minus 12y equal to e to the power minus 3x. This is general equation. Here I am writing d2y over dx2 and plus p1 dy over dx and plus p2y is equal to q. E to the power is equal to q. So this is same as equation this. This equation can be written as d square minus d minus 12y equal to e to the power minus 3x. Now solution. We are solving this equation. This problem 3, linear differential equation with constant coefficient. So d2y over dx2 minus dy over dx minus 12y equal to e to the power minus 3x is equation 1. Equation 1 can be written as d square minus d minus 12 into y equal to e to the power minus 3x. This is equation 2. Now, we find out the solution of 2. Here, we find solution of equation 2 in two part. Y is equal to CF and plus PI. So first find CF putting Q equal to 0. Q equal to, what is Q here? Q is e to the power minus 3x. E to the power minus 3x, this taking 0. Then equation becomes this one, d square minus d minus 12 into y is equal to 0. This equation 3. Putting here d equal to m and removing y from 3. Then we get an auxiliary form. Auxiliary form. So here m square minus m minus 12 equal to 0. Factorizing this, m square minus 4 minus 3 into m minus 12 equal to 0. M square minus 4m minus 3m plus 3m minus 12 equal to 0. So here factorizing here next, m is common, m minus 4, and next plus 3 common, m minus 4 equal to 0. So m minus 4 is common and m plus 3 equal to 0. So if m minus 4 is 0, then m equal to m1 equal to 4, and m minus plus 3 equal to 0, m equal to m2 equal to minus 3. So here value of m is 4 and minus 3. This is the value. So roots of m is different. Roots of an auxiliary form is different. So formula CF is equal to C1 e to the power m1x plus C2 e to the power m2x. So formula is C1 e to the power m1 means 4x and C2 e to the power minus 3x. This is CF. First part is complete. This is CF, complementary function. Now PI, particular integral. PI is equal to 1 upon FD into Q. 1 upon FD into Q e to the power minus 3x. 1 upon FD d square minus d minus 10. D square minus 12 into e to the power minus 3x. Okay, 1 upon FD. So PI is equal to, here putting d equal to minus 3. Comparing here, comparing e to the power ax equal to e to the power minus 3x. So a is here minus 3. Putting here 1 upon FD minus 3 का square and minus 3 and minus 12. So this is 1 upon plus 9 and plus 3 minus 12. So here 1 upon 12 minus 12. So here 1 upon 0. E to the power minus 3x, e to the power minus 3x, e to the power minus 3x, e to the power minus 3x. So here FD is 0 here. We are checking here FD is 0. So we change the method here. Condition we change here. Just this is rough work. We are checking here rough work. This result is 0. So using here, we are checking only FD. First we are checking only FD here. FD is 0 or not. So here FD is D square minus D minus 12. So FD, D is here, A is minus 3. FD equal to FA is F minus 3 equal to minus 3 ka square and minus 3 minus 3 and minus 12 minus 3 and minus 12. So this is plus 9 plus 3 minus 12. So this is 12 minus 12, this 0. FD is 0. So we apply here condition 3. Which condition apply here? Pi is equal to 1 upon D square minus D minus 12 e to the power minus 3x. This function taking to this side. So we write here e to the power minus 3x and putting D equal to D minus 3 ka square and minus D minus 3 and minus 12. So here writing 1 upon D square plus 9 and minus 6D and minus D and plus 3 and minus 12. 12 is cancelled. So here Pi is equal to 1 upon here D square minus 7D. D square minus 7D e to the power minus 3x. Here is only function 1 here. This function taking to left side. So e to the power minus 3x and here 1 upon D square minus 7D and here function is 1. So making binomial. Here making binomial here. Binomial. So lowest power of D is taking common. So here common e to the power minus 3x upon minus 7D and here is 1 upon 1 minus D by 7. So this equal to e to the power minus 3x upon minus 7 D and this term is taking in numerator 1 minus D by 7 whole to the power minus 1 and is opening this e to the power minus 3x upon minus 7D and now 1 plus D by 7 and plus D square by 49 and plus this and here function is 1 here. Function is 1. So 1 is taking. So all terms are 0 here. D square 1 is 0 and D 1 0. So all terms are 0 here. E to the power minus 3x upon minus 7D and here only 1. And e to the power minus 3x upon minus 7 and 1 upon D of 1. So 1 upon D Pi is equal to 1 upon D e to the power minus 3x upon minus 7 and 1 upon D into 1. 1 upon D is integration. 1 upon D of 1 means integration 1 dx. So that is x only. So this is e to the power minus 3x. Here is minus sign and here is x and upon minus 7. This is Pi. So y is equal to total CF. What is CF here? Minus 4, 3. So y is equal to CF is C1 e to the power 4x plus C2 e to the power minus 3x and plus Pi. Pi is this minus x e to the power minus 3x y 7. This is Pi. So here we find out the complete solution CF plus Pi. Y is equal to complete solution CF and plus Pi particular integral. Okay. So today I discuss how we can solve a linear differential equation of second order with constant coefficient. We apply the method of complementary function and particular integral. Basically solution of this linear differential equation in two parts. First part is complementary function, other part is particular integral, and particular integral depend on the value of q. So there are several cases arise here. Today I am completing my topic if q is exponential function only. In next topic we discuss this if q is algebraic function. Algebraic function means x square, x cube, x. If any some power of some variable x square, then what we are doing to find out pi. So this is the next topic. So here we be completing the topic if q is exponential function, how we can find particular integral. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.